Voyager 1's final images were never supposed to exist because the camera had been shut down for decades. Yet, when NASA decoded the last fragments that slipped through the fading signal, faint shapes and distorted patterns appeared inside the data that no one expected to see. Now, scientists are forced to stop and question what the spacecraft actually reached beyond the edge of the sun's protection. Error in the dark. For years, Voyager 1 sent back the same steady rhythm of numbers, and that consistency gave the team a sense of comfort. It was not perfect, but it was predictable, and predictability is rare for a machine drifting far outside the sun's protection. Then, in November 2023, the stream changed in an instant. The clean telemetry fractured into scrambled patterns that did not match any known system, and the shift arrived so suddenly that several engineers froze at their screens. Nothing about the data looked familiar, and the silence that followed carried its own weight. The first suspicion was a memory failure inside the flight data subsystem, a part of the spacecraft that decides how every piece of information is arranged before it leaves the antenna. A fault there can spread quietly because the system touches almost every instruction the probe sends or receives. If it collapsed fully, the mission would end without warning. Repairing the problem required the kind of patience that only deep space work demands, because each command needed almost 45 hours to make the round trip. Engineers returned to code written in the late 1970s and moved through it line by line, guiding fragments into the few memory locations that still responded. Every attempt felt like a single step taken across thin ice, because the wrong change could silence the spacecraft forever. Days passed in this slow cycle, and no one knew how many more the probe could endure. Yet the team continued, because letting Voyager fade without trying felt harder than facing the risk of failure. Then, on April 20th, 2024, the signal shifted again. The telemetry aligned cleanly, and the first lines showed the repair had taken hold. A wave of relief moved through the room, but it lasted only a moment because several packets inside the stream did not belong to any health report. They carried patterns that resembled fragments of imaging data, even though the camera system had been shut down for more than 3 decades. The room grew quiet again, but for a different reason this time. If the imaging pathways had produced anything at all, then something inside the spacecraft had awakened at the exact moment it nearly failed, and now the team had to understand what that meant for a probe drifting alone in the dark beyond the sun's reach. A dying circuit. The fragments that appeared in the restored signal did not resemble the clean photographs Voyager once sent during its tour of the outer planets. They were faint, uneven, and shaped by distortion, yet they held a structure that stopped the analysts who first saw them. The patterns were too deliberate to dismiss as random noise, and the gradients inside the frames shifted in ways that seemed to follow the environment rather than the spacecraft. Some researchers suggested that the memory fault had briefly reactivated parts of the imaging system, even though no command had been sent to wake it. Others believed the data came from a mixture of degraded camera pathways and plasma readings that crossed inside the damaged memory. Both ideas were possible, yet neither explained why the patterns appeared with more intensity than older background distortions. The timing made the situation harder to ignore. These shapes emerged only after the spacecraft survived a fault that should have silenced it, and they grew clearer as the repaired memory began to stabilize. It was unusual enough that several engineers went back through earlier telemetry, hoping to understand whether the spacecraft had been drifting into a region where normal behavior breaks down. The working theory soon shifted toward the environment around Voyager because the patterns resembled changes the probe had already recorded in its plasma sensor. The gradients lined up with small shifts in particle density, and the curved streaks matched the pressure fluctuations that had been growing stronger over recent years. This meant the images, if they could be called that, were not meaningless artifacts. They were linked to the same forces shaping the region Voyager had entered. Even if the true explanation is simple, the emotional weight of the discovery was hard to ignore. A spacecraft that had been silent for decades in its imaging circuits had responded at the exact moment it nearly died, and it delivered data that hinted at a landscape no mission had ever seen. It raised a quiet question across the team. If these patterns were real, then what exactly had Voyager encountered at the edge of the sun's fading influence? Ghost data. Voyager 1 was never expected to send back anything resembling an image at this stage of its life. The camera system had been shut down more than 30 years ago, and most of its supporting circuits had survived far beyond their intended lifespan. Many of the internal pathways that once handled imaging commands were believed to be permanently inactive, and the team had long assumed that radiation had weakened the hardware to a point where it could no longer respond. What complicates the issue is that the spacecraft was never designed to operate for nearly half a century, and the internal layout of its systems reflects engineering logic from the 1970s rather than the modular clarity of modern spacecraft. Subsystems depend on one another in ways that are not always obvious, and faults can cause signals to leak across channels that no longer follow their original design. Once radiation begins flipping bits and weakening circuits, the boundaries between functions become less certain. This is why some researchers believe the final frames were produced by hybrid telemetry rather than a true camera activation. When corrupted memory overlaps with environmental readings, the spacecraft can generate patterns that mimic image fragments even though no camera lens is involved. The surprising part is that the shapes inside Voyager's last frames lined up closely with plasma changes recorded by its functioning sensors at the same moment. The patterns were not random, and they moved with the same rhythm as the surrounding environment. This connection forced the team to reconsider how much information a failing system can still carry when the environment around it becomes unstable. If the region beyond the heliosphere contains sharper gradients or stronger pressure shifts than expected, those forces can influence every part of the spacecraft's signal. It also raised a quiet concern. If the environment had been changing this quickly, then Voyager may have been hinting at these conditions long before the images appeared. As engineers traced earlier readings, they found small variations that had been easy to overlook when the signal was stable. These subtle shifts now appeared to be part of a larger pattern, one that suggested Voyager was entering a region where the interstellar medium behaves differently than models predicted. The possibility added a new layer of meaning to the final frames, because they might not have shown a failure at all. They might have shown Voyager crossing into a part of space no spacecraft has ever measured directly. Consequences of Saturn. The strange part about Voyager 1's final images is that they were shaped by choices made long before the spacecraft ever reached deep space. The people who designed the mission in the 1970s built a probe meant to survive a 5-year journey, not a 50-year odyssey, and every step the spacecraft takes today still traces back to decisions made during those early years. The rare planetary alignment that occurs roughly once every 175 years created a path through the outer solar system that no mission had followed before. Jupiter, Saturn, Uranus, and Neptune formed a sequence that allowed gravity to act like a chain of slingshots, giving Voyager more speed than its own engines could ever produce. NASA took advantage of this alignment because it was a unique chance to explore the giant planets, but that decision also set Voyager on a course that would eventually carry it beyond the Sun's protective reach. Everything changed during the Saturn encounter. Scientists wanted a closer look at Titan, a moon with a thick atmosphere that could reveal clues about early Earth, and choosing that flyby bent Voyager's trajectory upward and out of the plane of the solar system. It locked the spacecraft into a path that removed any chance of visiting Uranus or Neptune, but it guaranteed that Voyager would one day be the first machine to reach interstellar space. No one realized how important that decision would become decades later, because it placed Voyager at an angle where the outer boundary of the heliosphere is not smooth or symmetrical. Models suggested that this region could be more uneven and turbulent, shaped by magnetic pressure and shifting plasma that collide in ways no mission had measured directly. That means Voyager's route takes it through a section of space where conditions may change more sharply than expected, and the patterns inside the final images carry the same uneven signatures predicted for this region. This creates a quiet symmetry in the story. A choice made in 1980 to study Titan more closely now shapes what Voyager sees at the edge of the Sun's influence. And to understand why the final frames behaved the way they did, the team had to look at what happened after the spacecraft left Saturn behind and entered a part of space where many of our earlier predictions began to drift away from reality. Across the fading solar wind. When Voyager 1 left Saturn behind, it moved into a stretch of space that looked empty from Earth but carried far more structure than anyone once believed. The spacecraft began picking up small changes in the solar wind, and those early shifts felt minor at first, the kind of fluctuations engineers had seen before. But as the months passed, the data settled into a pattern that did not match earlier missions, and the readings suggested the environment was starting to thin and change in unfamiliar ways. The solar wind slowed slightly, then slowed again, almost as if the long outward flow of charged particles was meeting resistance from something farther ahead. The magnetic field stretched into uneven strands, and bursts of high-energy particles began appearing in places where earlier models predicted calm. Each new reading added a small piece to a larger puzzle, and over time, the puzzle began to form a shape none of the original predictions had described. The most striking part of this transition was its gradual nature, because nothing dramatic happened at first. Voyager moved through regions where the solar wind grew weaker by small degrees, and the changes seemed gentle until the trend suddenly sharpened. It was as if the spacecraft had crossed an unseen threshold where forces from inside the solar system pressed directly against pressures coming from the interstellar medium. From Earth, these discoveries arrived slowly. Every transmission took long hours to reach the deep space network, and by the time each piece of data was analyzed, Voyager had already moved deeper into the region that produced it. This delay created tension because scientists were learning about the environment after the spacecraft had already passed through it. They could only watch the readings build layer by layer, revealing a boundary that did not behave like the smooth gradient they once expected. The growing unevenness in the data soon became impossible to ignore. The same shapes that would later appear inside the final images were present in the particle readings from this period, though far weaker. Pressure increased in one moment and eased in the next, and the magnetic field shifted with a rhythm that suggested the spacecraft had entered a place where the sun's influence no longer behaved in any familiar way. And all of this led to the moment the team had anticipated since the mission began, the point where Voyager would reach the edge of the heliosphere and step into a region no spacecraft had ever crossed. The signals hinted that the environment ahead was changing faster than expected, and that the boundary they once imagined as a soft transition might instead be shaped by forces far more abrupt and complex. Two winds collided. For decades, researchers believed the solar wind would fade gradually. But when the spacecraft reached the boundary, the readings changed almost instantly. Solar particles dropped away in a single step, while high-energy particles from outside the solar system surged upward at the same moment. The data arrived with such a sudden break that some engineers suspected an instrument fault because the shift looked too precise to come from nature alone. But the patterns held steady across multiple transmissions, and the numbers left little doubt that the spacecraft had crossed into a region shaped by pressures stronger than anything inside the heliosphere. It revealed a boundary that did not behave like thinning air, but instead acted like a compressed shell where two forces met in a narrow and unstable zone. Once Voyager stepped outside that bubble, it entered an environment that was anything but empty. The spacecraft detected a persistent tone around 3 kHz, a low and steady hum created by interstellar plasma waves vibrating in the space around it. This sound remained present for years, and its consistency showed that the region beyond the heliosphere carries more structure than anyone expected. The magnetic field outside the boundary also proved stronger and more complex than earlier predictions. Instead of a gentle extension of the solar field, Voyager found a region where magnetic pressure pushed inward with enough force to reshape the heliosphere itself. The field appeared 2 or 3 times stronger than the early estimates, suggesting that the sun's domain is squeezed from the outside by a galaxy filled with stirred-up plasma and tangled magnetic lines. These discoveries forced researchers to rethink the entire shape of the solar system's outer edge. The data suggested that the sun sits inside a larger structure called the local bubble, a vast cavity carved long ago by ancient supernova explosions. The pressures within this bubble bend the heliosphere's boundary in ways that earlier missions could only guess at from far inside. The unexpected patterns inside Voyager's final images line up with these same forces. The gradients resemble compressed plasma, and the curved streaks match the kind of magnetic tension the spacecraft recorded during its crossing. This raised a new question within the team, because the final frames did not behave like random distortions. They behaved like faint signatures of a region where the interstellar medium becomes more turbulent than expected. And as scientists examined those fragments, the idea grew harder to dismiss. If the spacecraft captured these patterns during a moment of extreme environmental change, then the final images might not show a system failing. They might show Voyager entering a layer of interstellar space where no other mission has ever had the chance to measure what lies ahead. Silent camera. Voyager 1's camera system was never expected to respond again because the team shut it down after the pale blue dot photograph in 1990 and disconnected the hardware to preserve power for other instruments. The wiring behind those circuits has spent nearly half a century absorbing radiation in deep space, and most engineers assumed the imaging pathways had degraded to the point where they could no longer carry a usable signal. Yet deep space hardware does not always fail in clean or predictable ways. High-energy particles can flip memory bits, corrupt instructions, or activate dormant circuits in patterns that no longer follow their original design. Once the flight data subsystem began experiencing memory faults, it created the conditions for old imaging lines to send out fragments of data that resembled image packets even though no camera lens had been activated. This effect is known as hybrid telemetry, and it occurs when degraded camera instructions overlap with environmental readings inside the same data stream. The result can look like a low-resolution frame, even though no optical system is involved. What made this case more unusual was how closely the shapes inside the final frames matched changes detected by Voyager's functioning plasma and magnetic sensors. The gradients shifted with the same timing as the surrounding environment, and the curved bands aligned with pressure fluctuations the spacecraft recorded at the same moment. Random noise does not behave that way. True noise scatters across the frame without direction or structure, and it changes from one packet to the next without any connection to the outside environment. The patterns Voyager produced in 2024 moved with purpose, following the same rhythm as the data from its active instruments, which suggested the frames carried information shaped by forces in the region around the probe. This possibility shifted the tone of the investigation because it implied that the failing camera system had not simply produced meaningless artifacts. It had reacted to the environment in a way no one had expected, revealing faint signatures of plasma density and magnetic pressure through pathways that should not have been capable of responding. If this interpretation is correct, then the final images may not show the stars or the void. They may show how the interstellar medium bends and drifts around a lone spacecraft crossing a region no mission has entered before. And this raised a new question within the team. If the images carried the imprint of real environmental changes, then they might not only tell us how Voyager is failing, they might tell us where the spacecraft has gone and why the surrounding space began shifting so sharply in the moment the fault occurred. Last light in the signal. When the final frames first reached analysts outside the Voyager team, the reaction was cautious because the shapes inside them looked unfamiliar and carried no clear structure at first glance. They did not resemble stars or dust or distant objects, yet the gradients moved with a steadiness that did not match random noise, and that alone made several researchers pause. Noise fades and scatters without direction, but these patterns shifted with a rhythm that pointed to forces acting on the spacecraft itself. As the data circles widened, scientists began comparing the frames with Voyager's plasma and magnetic readings, and the match was hard to ignore. The arcs inside the images lined up with pressure changes recorded near the heliopause, only now the signatures were sharper and more defined than earlier measurements. This meant the probe had likely entered a region where the interstellar medium was changing more quickly than expected, and the idea unsettled researchers who spent their careers studying the edge of the sun's influence. Several interpretations emerged. One idea suggested Voyager had moved into a compressed layer of plasma inside the local bubble, the vast cavity carved out by ancient supernovae that surrounds our solar system. Another possibility involved the galaxy's magnetic field, which bends and folds across enormous distances and can create narrow regions where charged particles gather and move in unexpected ways. A smaller group considered whether Voyager had crossed into a boundary within the bubble itself, a place where dust and magnetic structures settle into layers no mission has ever had the chance to map directly. None of these explanations were confirmed, yet each carried enough weight to draw attention far beyond the scientific community. People expected the spacecraft to fade quietly as its power declined, not to reveal signs that the region ahead might be more complex and more turbulent than any previous model suggested. The emotional impact came from the timing as much as the data itself, because the frames appeared only after a fault that nearly silenced the probe forever, and the coincidence made the fragments feel like a last, unexpected message from a machine nearing the end of its strength. For many observers, the moment felt larger than the science behind it. Voyager had spent almost half a century traveling through darkness, sending its faint signals across a distance so vast that each exchange took nearly 2 days to complete. Now, just as its systems began to fail, it revealed patterns that hinted at a new layer of interstellar space, a place shaped by forces the mission was never designed to witness. This is why the images stopped the world for a moment. They reminded people that even a dying spacecraft can reveal something that shifts our understanding of where the sun's influence ends and where the galaxy begins. And as researchers studied the fragments more closely, a quiet realization settled across the team. The frames may not be Voyager's final mistake, but its final discovery, arriving at the exact moment the spacecraft drifts into regions no model can fully describe. What lies ahead for Voyager is unknown, and its power will continue to fade, yet the last images suggest that the space around it is still changing. They may be the final glimpse of a frontier we will not reach again for generations, carried home by a machine that continues to push deeper into the dark long after it was expected to go silent.